Okay, lecture 25, mean and standard deviation revisited. Okay, and so we have there in the notes that you see the setup, we have the same random variable x and the same random variable y that we had last time. Random variable x was a continuous random variable that could take on all values between 1 and 9, and it was uniform, so its PDF went straight across. And the PDF for the random variable y was a discrete random variable. It could take on all the values between 1 through 9, all the whole number values, and so its histogram is given there. What I say first is pause and find the mean of y. So please pause and do that. Okay, if you've paused and done it, great. I'm not going to do it. Next one, pause and find the variance and standard deviation of y. Pause and do that, please. I'm also not going to do it. I think you're at the point where you should be able to do those yourself. Okay, now I point out that something we talked about a while back, that if we're talking about a data set, about typically 95% of the data will lie within 2 standard deviations of the mean of the data set. Right? If you remember, we looked at the situation where we had data sprawled across the real number line, and if you went to the mean and went up and down 2 standard deviations, it looked like you got roughly 95% of the data. That's not always true, but it's often true that you get close to that. And I point out that the same thing is often true for a random variable, right? We're talking about random variables here, not data sets. But it's also true that typically if you find the mean and go up or down 2 standard deviations, you usually will grab around 95% of all the values that the random variable, you grab 95% of the probability of the random variable in that region, roughly. And I think what I say here is, in this case, in the case of the random variable y, you should have the mean calculated. So go up there on your chart. I guess I can put it up. We have it here. Yeah. So go up and where you get the mean and go up and down 2 standard deviations, however far that takes you, and look at how much of the data you grab. All right, it's not going to be exactly 95%. Of course, it's a discrete random variable that goes up by like 1/11 or by 1/9 every time, right? By about 11% every time. So you're not going to get exactly 95%. Question is, what do you get? What percentage do you get of the data? And I'll leave you to figure that one out. All right, now I want to point something out there at the bottom of the first page. It's also possible to compute the mean, the variance, and the standard deviation for a continuous random variable. But that's going to be done in a different way, right? Because the way we do it for a discrete random variable, we make the chart, right? We have our random variable, in this case it's y, and then we have our p of y, and we have our values, and we have that, and then we do y times p of y, and we get those values, and we add them up, and there's the mean, okay? We can't do that for, this is discrete. We can't do that for continuous. Right? We don't have a way to write this chart. And I told you before, I think, that you can do it with some more advanced mathematical techniques. You can do it using calculus. That's not part of this class, but I'm just going to tell you on the next page, if we use calculus, we can show that the mean, which again, you should understand that means, in a very real sense, the average value of all the values that this continuous random variable here, x, can take on, right? This is x, right? And over here, this is y, right? So all the values it can take on this infinite set of values, you should not be shocked to discover calculus shows you that the mean is 5. It's dead center. That's, again, not surprising. I got all this probability over here and all this probability over here. It evens out that the mean is 5. The standard let's go with a variance. That turns out to be 6/3, or 16/3 rather. And when you take the square root of that, excuse me, to get the standard deviation, you get I say 4 times the square root of 1/3, which works out to be about 2.3, et cetera, et cetera. Okay. So again, what I ask you to do is look at the values that lie within 2 standard deviations of the mean. So now we're on the x random variable. Start at the mean and go up and down 2 standard deviations. You might draw it out and ask yourself, how much of the probability of this random variable am I getting? Am I getting around 95%? Am I getting more, less, whatever? And this is not a hard question. If you just work through it carefully, you can get the answer yourself. I'm not going to do it for you. Okay, I want to go on to the next paragraph there, though, where whereas we can think about grabbing most of the probability inside some interval, we can ask questions about then the little bits of probability left on either side, right? All right, so what I say here is we'll often speak of, as we have already, unusually large or unusually small values of a random variable. And this is a concept that's going to become very, very important. And I say here, we've seen that we can arbitrarily declare that any data value that is more than 2 standard deviations above the mean in a data set or 2 standard deviations below. Well, if it's more than 2 standard deviations above, we can call it unusually large. If it's more than 2 standard deviations below, we can call it unusually small. We did that for data in a data set. We can do the same thing here for a random variable. We can declare a value of a random variable is an unusual value if it lies more than 2 standard deviations above the mean or more than 2 standard deviations below the mean. Okay, so we can use that kind of 2 standard deviation criterion for random variables as well. And I think I then say, using that criterion, look at the random variables, x and y, and tell me what values of x would be considered unusual by this criterion, what values of y would be considered unusual by this criterion. They're usual, typical, if they are within 2 standard deviations above and below. They're unusual if they're outside of that. So you should be able to figure that one out. I'm going to just, again, leave you to do that. All right. I say then that, where are we? Okay, so finally, there's another way to think about unusually high or unusually low values of the random variable. And I say here that what we can do is we can declare what I would call a cutoff probability. And that cutoff probability, I give as an example, is 5%. And we can just say a random variable value is unusually high if it's so far over to the right that only 5% or less of the probability lies to its right. We could say it's unusually low if it's so far over here that only 5% or less of the total probability lies to its left. Okay, and that 5% rule number is somewhat arbitrary, but we can just declare it right now. In the future, we'll declare it for different percentages. But right now, you see that we can sort of do that. We can say it's unusually high if I'm so far out here that there's just a little bit of probability to my right, or I'm so low that there's just a little bit of probability to my left. Okay, so the thing that I want to walk through then is, I say here, under the 5% rule, we see that for x, we have for unusually low values what? Let's suppose we were going to do the 5% rule here. So in other words, here is my random variable x, and here are all the possible values, right, from 1 to 9. I want to go, I said the mean is 5, I want to go so far left that the little bit that I have to the left, that area will only be 5%. Okay, how far do I have to go? Well, I'm going to go ahead and kind of draw it in, and then we're going to see how to compute it. So it actually is going to end up being about right there, I think. But think of what I'm asking for. So this is my what I would call my cutoff value. We'll later see that we call it a critical value. I'll just go ahead and say that. I'm writing right in my numbers. Sorry, I wasn't watching. Sorry, writing right into my numbers here, so it's hard to read. So let me just bring this down a little bit more. Okay, this is going to be my cutoff value, which I say later lecture I'll call it the critical value, for being unusually small. All right, and what is that value? Well, what I'm saying is I want this value on the x-axis, I want it to be that the area that I get to the left of it to be 5%, right? I want that area to be 5%. Well, it's 5% of 1. So it's just 0.05, right? I want this area in this little strip to be 0.05. So look at what I want. I have this little rectangular strip. Its height is 1/8 because it's 1/8 all the way across. Its area is 0.05. I just don't know what the width is. What is the width? So let me just put here the width equal W. And here's what I'm going to do. I'm going to say W times 1/8 equals 0.05, right? Width times height equals area. I'm not going to write that down because I'm going to get too cluttered. You might want to write that down though. Width times height equals area. We've done these calculations already. To clear this out and see what W is, I multiply both sides by 8 and I get 0.4. All right, so what is this value? The width right here is 0.4. So the cutoff value starting at 1, I'd go just add an extra 0.4, and so it's 1.4. All right, so under the what I'm calling the 5% rule, let's say it like this: any value, any x value of 1.4 or lower is unusually low. Okay? Sorry, I'm kind of writing into my other graph there, but that's all right. All right, what about unusually high? Unusually high cutoff for x. You figure it out. I think I have you, yeah, there's a blank there for you. I think I will let you figure it out, all right? And I have written over my graphs here, but I can magically make the graphs go away, so it's a little easier to see. Okay, I'll let you to figure it out. It's not that hard. Same way of doing it. You have to just come up with the right rectangle and then figure out how much that is backed away from 9, right, which is the right endpoint. That's the farthest to the right. Okay, and so I just want to end by saying that the key here to understand is that what we're doing is we're making sure that the area to the left or the area to the right is sufficiently small, because for continuous random variables, probability equals area under the PDF curve. And we'll stop there.